Alrighty, chemistry, here we go. Jumping into another flipped lecture. Now we're continuing a conversation of how fast do reactions occur. And in this lecture, we're going to look at reaction mechanisms and rate laws. Now, some of this gets really somewhat convoluted, and I'll just be honest with you. I also need to confess that when I wrote this lecture, I was kind of a little bit in a loopy mood, and I went a little bit meme crazy, but that's okay. Humor is good, and hopefully that helps you understand as your endorphins are up because you're laughing. So we're jumping into reaction mechanisms. I expect to get a lot of questions about this tomorrow, but that's okay. I'm going to do my best for you right now, and then we will slog through it together. Here we go. A balanced equation may not show all of the steps in a chemical reaction. And you go, what? I thought that's what reactions were about. Yeah. They give you the first part and the last part, and then they kind of skip the stuff in the middle, because all the stuff in the middle, it doesn't matter, really, but it does when you're looking at the steps involved in the reaction. Then you need to care about all the stuff in the middle. So what we have to do is understand that there are some substances that are made and then destroyed immediately in the chemical reaction. Those are called intermediates. And so the same atoms or electrons may bond in several ways before their final arrangement in the products. So just understand, we're at this moment going to be looking at intermediates and how things happen. So in this particular picture, what I want to show is that there are lots of ways that reactions can actually happen the way that it actually plays out. And this is supposed to be an animated little picture that's not animating for me right now, and I don't know why. But when this molecule connects to this molecule, there's some bending in this because of the addition of another part of the molecule, and this bending facilitates the joining of this. But there's all kinds of bending and twisting and turning and folding that happens to make the reaction happen, and parts jump off of one molecule and land on another, and there's it looks kind of like a wrestling match, honestly, when you look at what chemical reactions actually look like when they happen. And so when we try to ask questions about how is this occurring and what makes it happen faster or slower, it gets a little bit, well, scary. Yeah. It's okay though. It's okay though. We'll get through it together, right? We will, I promise. Yeah, I'm strange. I know. It's okay. All right, so of all the steps in a reaction, usually only one determines how fast it goes. There are usually reaction steps that happen really quick, boom, 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 and then there's something that it waits on. And that step it waits on controls the speed of everything else. It's kind of like the weakest link, right? The weakest link in a chain determines how strong the chain is. The slowest step in a chemical reaction determines how fast the chemical reaction is. And that one step is called the rate-limiting step. It's the step of the chemical reaction that takes the longest, and so everybody else waits around for that to happen. Once that happens, everything else can occur, okay? The concentrations of the reactants of this step control how fast the whole process goes. So if a reactant is doing something and another reactant is sitting out here on the side not involved, and this is the limiting step, then this guy out here doesn't matter. At least when it comes to asking the question, how fast does this occur? It still matters, because you got to have them to do the reaction, but it doesn't matter when we ask how fast is the reaction happening. So the concentration of the reaction of the limiting step is the rate-limiting reactant. And that's the thing that we've got to get at and see, how does the concentration of that thing mess with the rest of the speed of the reaction? Okay, so we have an expression called a rate law. A rate law is not something that is passed by a government. A rate law is just a mathematical expression of the thing that controls how fast a chemical reaction happens, okay? We use a value of an unknown constant. We use the letter K for a reaction constant for this particular reaction. K is different for every reaction, just like delta H or delta S. You just have to look it up, okay? You can also calculate it experimentally, but it isn't something that you can determine beforehand. So it's something that you've got to determine experimentally, or if somebody else tells you this is the rate law, you can know what the rate law is, okay? Concentration of the reactants in the limiting step. And so for the reaction, C4H9Br plus water gives you C4H9OH plus H3OH. This is a problem of the ionization of water here, and this C4H9Br is grabbing a hydrogen, a hydroxyl group, and leaving the water to ionize itself with the leftover hydrogen, right? When we look at this, we have two reactants and two products. And there's two steps to this reaction. There's rip a hydroxide off of the water step, and then there's ionize the water step. And when we experimentally determine this, we could say that the rate law is K times the concentration of C4H9Br. And what we're saying is that the more you concentrate this reactant, the faster the reaction is happening. Notice there's no water here, right? Water doesn't matter in this particular reaction. Its rate step does not control the rate of the reaction. The ionization of water happens instantaneously, and what we're waiting on is the theft of the hydroxide from the water group. Okay, so the concentration of this is the only thing that matters that controls the rate of the reaction. Okay, for now, we're not going to worry about the concentration of the products. They will come into play later. But for this moment, we don't care about the concentration of the products. Okay, and the value of K, again, always determined experimentally, and it's different for every reaction. And unless somebody has told you what it is, you need to figure it out after you've done the reaction, actually in the lab. Okay, so this whole thing is called a rate law. That's what that mathematical expression is called. So now, not every reactant in a rate-limiting step influences the rate equally. Even if you get all the reactants of just that one rate-limiting step, sometimes an individual reactant processes faster, processes instantaneously, doesn't slow anything down. Increasing or decreasing its concentration doesn't control the speed of the reaction. So we can call reactants that do not influence the speed of a reaction a zero-order reaction. What that means is we raise it to the power of 0. What happens to any number that you raise to the power of 0? It turns into 1. So when we are talking about a mathematical expression, and we have the concentration of this thing times the concentration of this thing raised to the 0 power, that's just the concentration of this thing times 1, which is an identity, right? It is itself. So anything raised to the 0 power, a zero-order reactant, does not impact the speed of the chemical reaction. If we don't give it an exponent, we assume that it's a 1, and that's true of all math. Any number where we don't have an exponent, the exponent is assumed to be 1. So in all of these other examples, the concentration of C4H9Br is 1. It's a first-order reactant. The more we increase the concentration, proportionally, the speed of the reaction will increase as well. There are some examples where there's a 2 up there, or a 3, right? A second-order reaction. What that means is that the more we increase the concentration of, in this case, nitrous oxide, it actually doesn't increase the reaction rate proportionally, it increases it exponentially. So if I double the concentration of nitrous oxide in this particular example, the reaction rate actually goes up by a factor of 4. It goes 4 times faster if I double the concentration. There are such things as third-order reactions. There are fourth-order and fifth-order reactions. And generally speaking, the larger this is, the more important that reactant is to the overall rate of reaction. So the powers, the orders of reaction in the chemistry terms, control how much that concentration influences the reaction rate. Okay? So a couple more things. In a simple single-step reaction, which is some of the reactions you will deal with, the coefficients of a balanced reaction predict the rate order. So nitrous oxide plus bromine gives you nitrous oxide, nitrogen and oxygen and bromine. I don't actually know what that would be called. NOBR, there you go. The coefficient in front of the 2 actually becomes the exponent. So you can predict in some reactions, you can see a coefficient of a 2 and be like, oh, I bet that's a second order reaction. That doesn't always work, but it's a good way, it's a good starting point, it's a good hypothesis to begin at and then test to see if that's right. Okay? So let's do an example together. Yay, reaction rate. Here we go. One of the most amazing reactions to watch is the thermite reaction. I'll show you a picture of it in just a moment. Where one oxidized metal is reduced by the oxidation of a more reactive metal. So you have metal number 1 that is an oxide, and you have metal number 2, and we're going to reduce and oxidize at the same time, and it gives off truckloads of heat energy. It's really cool. And one example of the thermite reaction, thermite is not a thing, by the way, it's the name of this reaction, is iron oxide plus aluminum. And when you get that thing hot enough to react, you overcome a rather monstrous activation energy. You get a stupidly beautiful explosion, fire, white smoke. It's amazing. But we have determined that the rate is independent of the concentration of iron oxide. No matter how much iron oxide you have, it doesn't speed up the reaction. It's only the aluminum. Okay. Also, the rate went up by a factor of 8 when the concentration of aluminum was doubled. Express the rate law. Okay, so we've got to think about what we have here. Iron oxide doesn't matter. So that means that the iron oxide concentration is going to be 0 order, right? And then the aluminum does matter, and we were told that the rate went up by a factor of 8 when the concentration of aluminum was doubled. So we've got to think about that. What is the exponent, right? We don't need to write down the iron oxide, and she understands. I hope you do too. How would we express that the rate went up 8 times when the concentration of aluminum is doubled? So doubling means that it's 2, right? Then the rate law went up by 8. How do you get from 2 to 8 by using powers, right? It's the 2 to the 3rd power is 8. So that means that we must have the concentration of aluminum be raised to the 3rd power. Notice this simple reaction, you might predict that it's 2 to the 2nd power. Oftentimes that works. It doesn't always work. So we have 2 to the what is 8. 2 to the 3rd is 8. So I don't know why everything's highlighted all of a sudden. So the rate law is the concentration constant times the concentration of aluminum raised to the 3rd power. And now Jack Sparrow understands, and I think you do too. Let me just show you this reaction real quick because it's totally fun. Again, not my video. I don't own this, but it's cool, and I'm going to watch it with you. Here we go. 6 minutes long. We're not going to watch the whole thing, but please play. Pause. So little bit of fire to get it started, but once it goes, boy howdy does it go. And it burns through not just the fuel, but through the can, and actually through the brick. You can see that the fire is going down all the way through a brick that it's sitting on. And this video shows multiple examples of the thermite reaction, and we're not going to watch them all, but some of them get really cool. Here's one. Thermite versus a computer scanner. That's pretty cool. Blows the thing to smithereens. All of that heat and all that fire, of course, it's a massive delta G difference. And so it's giving off all this reaction. And anyway, it's just fun to look at. I'm a guy, I like fire. If you have any questions about chemical reaction rates and rate laws, please put them in the comments field below, and I'll get to them as quickly as I can. Otherwise, I'll see you in class tomorrow, and we'll continue to talk about chemistry and play with all these concepts. Unfortunately, we're not playing with thermite. Fire department doesn't want to come to our rescue. But anyway, God bless you, and hope you understand it all. I'll see you tomorrow. Jesus loves you, and so do I.